Okay, so let me briefly go over these questions. First question was evaluate, using Euler's theorem, 5 to the 3103 mod 64. Using Euler's theorem is if the GCD of A and N is 1, that is if A and N are relatively prime, then A to the phi of N mod N is equal to 1, where phi of N is the number of numbers less than N relatively prime to N. All right, so we have N is in the position of 64, and our A is 5, so we want 5 to the phi of 64, and that will help us find 5 to the 3103. So what is phi of 64? Well, as it turns out, all odd numbers less than 64 are relatively prime to 64, because the only factors of 64 are powers of 2. Now, every other number is an odd number, so that means you're counting to 64 by 2s, and you have 32 numbers. 32 odd numbers, rather. Okay? So that's what my phi is. The 32 is phi of 64. So let me just indicate that. This 32 is equal to phi of 64. Oh, that's what it says here, phi of 64. All right? All right, so we know that 5 to the 32 is congruent to 1 mod 64. So what we want to do is write this 3103 in terms of 32. So if you divide 3103 by 32, you can use your hand calculator for that. But then you get that 32 goes into 3102 3,072 times, but there's 31 left over. Now, we know this is a multiple of 32, so this 5 to the 3072 is actually equal to, let's see if I can get this working here. It's equal to 5 to the 32 to the 96 power, but this is congruent to 1. So this is congruent to 5 to the 31, okay? So you want what's 5 to 31 is congruent to what mod 64? Well, notice something. If I take 5 times 5 to the 31, well, that's congruent. That's equal to 5 to the 32, and I know that's congruent to 1 mod 64. Okay. So what I need to solve is I need to find the number that when I multiply by 5, I get 1 mod 64. So I'm looking for 5 times x is congruent to 1 mod 64. Okay. Now you could do this by trial and error, or you can use the method that we talked about in number theory. We have 5x equals 1 plus 64 times n. Then we divide both sides by 5. We get x equals 1/5 plus 64n over 5. Now we can write this as 1/5 plus 60 over 5n plus 4 over 5n. Now this is an integer because 60 over 5 is a whole number, it's 12. So in order to make x a whole number, I need to choose a value of n which is equal to which gives me a whole number here. All right, and you can see that if I have a 1/5 and a 4/5 n, I can see that n equals 1 gives me a whole number. So if I plug in n equal 1, I get x equals 1/5 plus, and then this is plus 12n, so that's 12 times 1 plus 4/5 equals 13. And you can check that 5 times 13 is equal to 65, which is congruent to 1 mod 64. Okay. All right, so our answer is that we have 5 to the 3103 mod 64 is equal to 13. Now I can say that this last step was somewhat difficult in order to go from this step here to find what 5 to the 31 is not so easy. But the important part of this problem was showing that 5 to the 32 is 1, So you can reduce this very large factor down to 1. That's the important part of this problem. If you couldn't get this part, that's not important. This is the primary importance, that you can reduce this enormous factor down to 1. All right, so let's go to the next problem. Next problem was give the Cayley table for U10 mod the cyclic group generated by 9. So what is U10? U10 is the numbers less than 10, relatively prime to 10. Let's see. So U10 equals numbers relatively prime to 10. Okay, and less than 10. So we have 1 is relatively prime, 2 is not, 3 is, 4 is not because they both have a common factor of 2, 5 is not, 6 is not because a common factor of 2, 7 is, 8 is not common factor of 2, and 9. Okay. So that's U of 10. Okay? All right, now we need to know what 9 is. 9 is equal to the cyclic group generated by 9. So I start with 9. Now this is a multiplicative group. Right? The U groups are multiplicative groups, so I have to take 9 times 9, and I have to keep going until I reach 1 again. Now it turns out that 9 times 9 is 81, which is 1. So all it is 9 and 1. That's what the cyclic group generated by 9 is. Okay? So if I want the index of 9 in U10, well, it's equal to the number of elements in U10 divided by the number of elements in 9. So that's 4 elements in U10, 2 elements in U9 equals 2. So that means there are 2 cosets. So in 2 cosets in this. So this is not going to be a big table. Okay? Now what are they? We always know that when we have a coset, the group itself is one coset. Okay, so 9 is equal to 1 and 9. Sorry, it's equal to 1 and 9. Now the other coset I can obtain by taking any element in U10 and multiplying by this coset. I should say any element that's not in the coset already. So the other coset is, I could take 3 times 9, which is equal to, well, if I multiply this by 3, 3 times 9 is 27, which is the same as 7 mod 10. Okay? So those are my 2 cosets. All right? So let's set up the Cayley table. One Cayley table is, I could write it this way. I could also write it in set notation. That's fine. The other coset is this one. Coset 9 here. Other coset with 3 and 9. 3 times 9. Now if I take any element in the coset of 9, multiply by any element in the coset of 9, I'm going to get the same coset. Okay? If I take any element in this coset and multiply by any element of this coset, I'm going to get this coset here. And same here. And if I take 3 times 9, 3 times 9, well, you can think of it as it becomes 9 times 9, but if you just try any element in 3 times 9, multiply it by any element of 3 times 9, you're going to get an element in 9. So here's your Cayley table, and that's your answer. Okay. Last question. Okay, let me grab it here. All right, consider a hexagon with vertices labeled from 1 to 6. Let D6 be the group of symmetries of the hexagon. Let S be the reflection that leaves vertex 1 fixed. Prove or disprove the subgroup IDS is a normal subgroup of D6. So I'll just quickly draw the picture. In this case, it's really not necessary to draw the picture, but let me go ahead and do that. This is a terrible hexagon. But anyway, I can label the vertices 1, 2, 3, 4, 5, 6. Okay. And S is the reflection that leaves 1 fixed. Okay. So in fact, S is going to take 2 to 6 and 3 to 5. Now we know that D6 has this form. It has the ID, R squared, R cubed, R to the 4th, R to the 5th. And then it has S, and then SR, and then SR squared, and then SR cubed, SR to the 4th, SR to the 5th. Okay. All right. All right, now, let's see. Now, let's take ID and S. So I'm going to take ID and S. So is this a subgroup? Well, let's see if the Cayley table works out. So we can take ID and S like this. And ID times ID is ID. ID times S is S. S times ID is S. S times S is what? Well, since it's a reflection, you do the reflection twice, you get ID. So it's a group. Okay. So now the question is it normal? Okay. So in that case, we have to show that the right cosets equal to left cosets. Okay. All right, well, let's try. Let's try the cosets. How many cosets are there? Okay. Well, it's going to be that's the index of this IDS in D6. So that's equal to the number of elements in D6 divided by, well, here there are 2 elements here. So this is 12 over 2. So there's 6 cosets. Okay. So let's look first at left cosets. Okay, now one of them is IDS. Okay, another one would be R times IDS. Which is the same as R and RS. Okay. All right, now I can continue down, but let me start listing the right cosets. Okay. All right, now one right coset would be IDS. Another right coset would be IDS times R. And that's equal to RSR. Right. Now, is RRS the same as RSR? And the answer is no. These are not the same. They're not the same. Okay. Now, we showed that not only you have to have left cosets equal to right cosets, but if you can show that R times, let me just call this subgroup G. If I can show that RG is not equal to GR, where G is equal to IDS. In this case, that means that the left cosets are not equal to right cosets. Okay? So G is not normal. Okay? So the key here is that you remember that RS is not the same as SR. Okay? So this left coset and this right coset are not the same, so the group is not normal. Now, some people said that the group is abelian. The group is not abelian because RS is not equal to SR. So it's not an abelian group. Okay, so that finishes problem 3.